that is the acceleration due to gravity with which something, if I drop, will fall. Suppose, though, the force of gravity on an object of mass little m would be given this way. The acceleration that it experiences would be given this way. Now, near the surface of the Earth, the value of r is about the radius of the Earth. So I could do an approximation. We could say the typical value we expect for g is this acceleration must be true when I use the radius of the Earth as the distance from the center. But if I want to consider how fast, for instance, gravity falls off as I go up, I could do a Taylor expansion of this function and look for the first correction. Alternatively, I can use the binomial formula, which we introduced last semester. So let me go for that. We have g as a function of r should be equal to g m over r squared, but I will write r as the radius of the Earth plus some little elevation z. Now, I'm going to imagine that the altitude z is small compared to the radius of the Earth, so I'll factor out the big term. And that is algebraically just an equivalence, except that now I look at this as 1 plus a small quantity raised to a power. And the binomial approximation, which Newton was mentioning, says that this is approximately equal to 1 plus n epsilon, and the next term would involve epsilon squared. So if epsilon is small, then the quadratic term might be negligible compared to the linear correction. So in this case, what is the power? N? Negative 2. It's sitting in the bottom. So here n is negative 2. And epsilon is z compared to the radius of the Earth. And so we get that g, correcting for elevation, is approximately g at, maybe I'll put g naught, the value at the surface of the Earth, times 1, and then minus 2 z over re. So if you don't go up very far compared to the radius of the Earth, your correction would be very modest. Anyone happen to know the radius of the Earth? The solid bits, or the ocean bits. Yeah. I'm going to go for 6,400 kilometers. Okay, so if we're moving around only a few kilometers, right, Everest is a few kilometers up, then to a rough approximation, or a pretty good approximation, we just have a single value of g. We'll see later how we want to refine that just a bit. Okay, it's demo time.